Hello and welcome to Screencast today about the Fundamental Theorem of Calculus. And this screencast is going to be focusing on power functions. Okay, so the Fundamental Theorem of Calculus, as I wrote out here, says that if f is a continuous function on the interval from a to b, and big F is any antiderivative of f, okay, because remember these come in families, then the integral from a to b of little f of x dx is equal to big F of b minus big F of a. Okay, so again, we're going to be focusing here on the idea of the antiderivative. So that is working our way backwards from the derivative. Okay, and we can always check our answers, because what you can do is just take the derivative of your answer and make sure you get back to where you started. All right, my first example here today says evaluate the integral from -1 to 3 of 3x squared minus 2x plus pi, and all of this is going to be done dx. So remember, that just means then we are integrating with respect to x. So x is going to be our variable. Okay. All right, we know f is a continuous function because it's a polynomial, so we don't have to worry about anything going funky there. So now we just need to find our antiderivative. Okay, so let's take it piece by piece, because remember, we can break this integral up, or we can just do like we did with the derivative. Whenever we have sums and differences, you can just do the antiderivative of each piece. Okay, so the antiderivative of 3x squared. So you've got to ask yourself, what function do I take the derivative of that will give me 3x squared? Okay, well, the power rule, remember, works in reverse. So that's going to be, we need to excuse me, leave our 3 out front. We add 1 this time to our exponent. And instead of multiplying that, we're going to divide it. Okay, and then hopefully you notice these 3's will cancel. So the antiderivative of 3x squared is x cubed. Okay, we can check that because the derivative of x cubed is 3x squared. All right, next piece. So minus, the 2 again comes along because it's a constant with our constant rule. Then we'd have x. Technically this is to the first power. So if I add 1, I get 2, and I divide by that, I also get 2. So again, those coefficients cancel. So the derivative, the antiderivative of negative 2x is x squared, and that's because the derivative of negative x squared is negative 2x. All right, and the last one, the constant here, plus pi. Well, so now we got to think to ourselves, all right, so what kind of a function must have a constant slope, because remember that was our derivative, of pi? Well, that's got to be a linear function, so that's going to be the function pi x. And again, if you take the derivative of pi x, do you get back to pi? Absolutely. Okay, so let me go ahead and pretty this up a little bit. Let me throw my endpoints on here. So we've got -1 to 3. So this antiderivative then is x cubed minus x squared plus pi x. And again, I'm going from -1 to 3. Okay. Now you notice the dx went away, the integral sign also went away. So these two pieces then are basically the integration idea. Okay, but those two pieces do not get carried along. They drop out whenever you do the antiderivative. Okay, plugging in our numbers then. So we're going to have 3 cubed minus 3 squared plus pi times 3. That's going to be our f of b basically. So this is the antiderivative evaluated at our top endpoint, minus, okay, now we definitely got to watch our negatives on this one. So I'm going to do -1 cubed minus -1 squared, and then plus pi times -1. So this big quantity here is my big F of a. So that's my antiderivative evaluated at my bottom endpoint of -1. Okay. All right, so anyway, crunch out some of these numbers. Let's see, so this gives us 27 minus 9 plus 3 pi. Okay, you want to leave that as exact, we can, or we can approximate it later. Then we have, let's see, -1 cubed will give us -1. Minus -1 squared, though, gives us a +1, and then that's going to be minus pi. Okay, so that gives us, let's see, 18 plus 3 pi. And then minus -2 minus pi. Combining our like terms, that gives us a negative and a negative, so this negative here has to be distributed, which is why I keep putting these parentheses in here. So that's going to end up giving me 20 plus 4 pi. So that's my exact value of my integral. If you just want an approximate value, though, this gives us about 32.57 if I crunched everything correctly. Okay. Fantastic. All right, next example. Again, evaluate the integral. This one looks a little bit uglier, though. So we've got the integral from 2 to 5 of 1 over the square root of p dp. Okay, so again, this dp here tells me that I am doing my integral with respect to p. Okay, well, if we were doing the derivative of this function, I think it was smart to rewrite this first. So same thing happens when you do integrals. So we're going to have the integral from 2 to 5, so those numbers don't change at all. And remembering the rules from algebra, we can rewrite this function as p to the negative 1/2, and then again that dp gets brought along. Okay, so now this looks more like a power. So I'm going to add 1 to my power, so that gives me negative 1/2 plus 1, so that's a positive 1/2. And then I'm going to divide by that number, so I'm dividing by a half, and that's my antiderivative. Again, I know this because if I do the derivative of this function, I'll get back to where I started. Okay, I'm evaluating this from 2 to 5. And if we pretty that up a little bit, that's 2p, actually let's go ahead and call it 2 square root of p from 2 to 5. So then that's going to give us 2 square root of 5 minus 2 square roots of 2. Okay, can't really do much with those. But if you want that to be an approximate value, that gives us about 1.64. Okay. Now you notice this one had an interval that was very well chosen, okay? Because if you think about this function here, 1 over the square root of p, that function is not continuous at 0 because it's not defined. But you notice 0 is not part of my interval on the integral. Okay, so that was very well chosen, and just always kind of make sure to double check those things as you're going. All right, thank you for watching.